a bunch of people with white lab coats, like doing research experiments. That's not math research. Math research is a lot of quiet thought and brainstorming and doing a literature search, which is like finding sources where other mathematicians in the past have written things that are important to your research. So that's why you should learn, that's why you should do undergraduate research, to learn about the process in which math research is done. And another thing is, let's say that you're an undergraduate student and you want to get a PhD, and you've never done research before, then most likely you're not going to get into that PhD program if you've never done research, because PhD programs look for students who have done research in the past. And I found online a statistic that said that on average people finish a PhD in 8 years, and on average they finish by the time they're 33. So this is a big commitment to make if you're going to go into a PhD program, and you should only make that commitment if you actually want to do research and you know that you enjoy research, because you don't want to drop out of that program. And the PhD program doesn't want you to drop out either. They want people who will stay in the program. So how I got involved in my undergraduate math research. So honestly, when I left high school, I didn't think that I would ever get involved in math research again. And it's not because I didn't enjoy math research. I actually loved my math research in high school. It was because I didn't know that undergraduate math research was being done. So in fall 2015, Dr. Silberger, the head of the math department, who's right there, she sent an email to all the math majors saying that Dr. Gonzalez, the newest faculty member, was looking for a new research assistant. And when I got that email, I got really excited because I love math research. And when I saw the responsibilities that this research assistant would have, I got like 10 times more excited because remember I said that I'm a math and computer science major, and I saw that one of the responsibilities would be programming, and I love programming, so that made me like 20 times more excited to do it. I didn't really know what a literature search was, but I figured, hey, I can handle that because I love programming, so why not? And another thing that made me really excited was that Dr. Silberger said that it could be used for the departmental honors requirement for an honors college person. So I'm part of the honors college, and I want to graduate with the highest designation in honors college, which is the honors college graduate with distinction. So in order to do that, I have to take a departmental honors course, and she said that I could use this research to do that. So that made me really excited to do research. And so keep in mind that the email that I got from Dr. Silberger was in the fall 2015, but by that time I had already registered for all my classes, so I couldn't take the departmental honors course at that time. So Dr. Gonzalez and I, we made a plan where I would just learn the basic background knowledge during my fall semester, and then during my spring semester, I would be doing the actual departmental honors research. So keep in mind that in the fall, I didn't really have much knowledge of probability and statistics, so I had a lot to learn. So each week, Dr. Gonzalez and I, we would meet up and go over a chapter that I had read in James Gentle's book, Random Number Generation and Monte Carlo Methods. And this book was very challenging for me because it had a lot of complex math in it, and it assumed that you had some knowledge of probability and statistics already. So I've always been used to in a math class where you get a math textbook and I'm able to effortlessly read it because math textbook just makes sense to me. But this textbook was very complex, and it was the first time where I got really nervous and uncomfortable, like, oh my God, I can't read this, I don't know what I'm gonna do. But each week, Dr. Gonzalez and I would go over any road bumps that I had come across while reading, and she would help me understand what exactly it was talking about, which helped me a lot. And even though I don't think that this book directly helped me with my research because it wasn't on my topic, generating uniformly distributed random variables on the d-dimensional unit spherical shell, but it did help me because it prepared me for the complex math that I would be looking at in my spring semester. And two concepts that I learned are the probability density function and the cumulative distribution function. And I was going to go over them, but there's like no students here, so I'm pretty sure all of you guys know what they are. Does anybody want me to go over them? Okay, so this is a PDF, the probability distribution function, and it's one thing that I learned in my fall semester while doing the research. And it's a function that shows the probability that a random variable will take on certain values. And the thing is that with the probability density function, that the probability of the random variable taking on one value is 0. And I'm talking about continuous random variables here, which means that they can take on an infinite number of values. And because of this, we are interested in a range of values. So, for example, here the probability that the random variable will take on a value less than or equal to A is the area under the curve here. And the cumulative distribution function is actually the integral, or the area under the curve of this function. So if you look here at A, the y value that corresponds is the area under the curve here. So now I'm going to talk more about what I've done in the research. So the objective of my research, we wish to generate samples that are uniformly distributed on the sphere of radius 1. So this may not make a lot of sense to visualize in, say, 4 or 5 dimensions, but I have pictures here for the second dimension and third dimension. And for the second dimension, we want to find points that are on the circle. So on the surface, not inside the circle. So, and also we don't want there to be big clumps like over here or over here. We don't want the probability that we'll get a point over here to be greater than the probability of getting a point over here. And then with 3 dimensions, we want to find points that are on the surface of the sphere, so here, 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 and not inside. And this has to work in all dimensions, not just 2 and 3. And there are methods that are out there currently for doing this. And my major responsibility was to find them online using literature search and also to program them. And the reason why we want to do this is because Dr. Gonzalez came up with a method to do this process, and we want to compare her method to the methods that are currently out there to see if hers is better than the ones that are currently out there. So during my winter break, I did a literature search, and I thought that this would be really easy. I thought like, oh, you know, on Google Scholar, I'll just type in the words, generating uniformly distributed random variables in the d-dimensional unit spherical shell, and all the results will just magically pop up because everybody's researching this topic, obviously. But I was very wrong because when I typed in those words, nothing really came up. And after hours of digging, I came across 2 methods. And the first one is using normal random variables and then scaling them so that the magnitude is 1. And then the second one involves spherical coordinates. And then I also found sources that were using these methods, so that seemed to suggest that there weren't any other methods that we were missing because we found recent sources that were using these methods. And again, the reason why I was doing this was to find all the methods that were currently out there, program them, and then compare them to the one that Dr. Gonzalez created. And hopefully hers would be better. So a little bit about the first algorithm is that we create a d by n matrix of normal random variables, where d is the dimension and n is the number of vectors that you want on the d-dimensional unit spherical shell. And then what you do is each column will be a vector that will be on the sphere, and you find the magnitude of each column, and this will be either less than or greater than 1 probably, but what we want is that we want to scale it so that the magnitude is 1, and then what we do is we scale it so it's 1, and then we transpose, which means that on the vectors the rows become the columns and the columns become the rows, and then this is based on the concept that if you have a vector and you divide by the magnitude, then you have a unit vector. So that unit vector will have a magnitude of 1, and it will be in the same direction as the original vector. And this is the code for the algorithm. And this was written in MATLAB, and MATLAB is very helpful for mathematicians. I tried writing this code in Java, and it was 3 pages, because in Java you have to use 2-dimensional arrays, and when you use 2-dimensional arrays with matrices, then none of the operations are built in. You have to do everything yourself, and that takes a lot of code to do. So I found that MATLAB was very helpful. So now in the future I'm going to use MATLAB instead of Java for math things, especially with manipulating matrices. So I have an example of going through this code and generating 2 vectors that are on the d-dimensional unit spherical shell. So I did n equals 2, which means that we're going to create 2 vectors. And I did d equals 3, which means that we're going to be on the 3-dimensional unit spherical shell. And the first thing that we do is we check the if statement if d is less than 2, which isn't the case because d is obviously not less than 2, it's 3, so we don't go in there. And then we set the matrix temp, and we make it equal to a 3 by 2 matrix of normal random variables. And I prepared beforehand some numbers that I got from MATLAB for this. And then the next step is that we are going to take the magnitude of each of these columns. And there's a lot of steps here, so I'm going to do it one by one. So the first thing that we do is we square each item in here. So like for example, negative 2.2588 squared is 5.10218. And then the next thing we do is we sum up each of the columns. And then the last thing we do is we take the square root of each of these numbers and we set that equal to the matrix called MAG. And then the next thing we do is that we create a dm, which is equal to the diagonal matrix of the inverses of the magnitudes, but first I'm gonna take the inverses and then I'm gonna do it step by step. So the first thing we do is we take the inverse, so we do 1 over each of these numbers. And then we set dm equal to the diagonal matrix that where the diagonals contain these two values. And then finally, what we do is the results, which is what is returned from the function, is said to be the transpose of multiplying the temp matrix and the dm matrix. Because when we do that, we're pretty much doing this, where we're creating vectors that have a magnitude of 1 with the same direction as the original ones. So I'll do it step by step. First, we're gonna multiply these two matrices. And then the last step is to take the transpose of this. So that means that the columns become the rows and the rows become the columns. So, and that's the result that we're going to return from this function. And then the final results are this and this. And if you had a calculator, you could calculate the magnitude of these and you would find that it's 1. And they are uniformly distributed on the 3-dimensional unit spherical shape. And this is the first method that I found online when I was doing my literature.
How do you know this is uniformly distributed?
What?
How do you know that this is uniformly distributed?
There was a proof also in the article that said that this works.
Yeah, so Stephanie still doesn't have the background to do those. She hasn't even taken probability yet.
Oh, okay.
So, but,
That's a
Yeah.
rather sophisticated fact, right?
right, I mean, I think that after taking probability, she can probably go through the proof, but, yeah.
Yeah, later on, I talk about the challenges that I went through when I was doing
Okay,
this, and
okay.
one of the challenges is that the proofs are very complicated, so
Uh-huh.
I just have to accept what the proofs say rather than being able to do the proofs myself.
I wouldn't know how to prove that one, so. Right.
I would settle for not knowing the proof, but making sure I understand the statement. So this may be sort of
Right.
obvious question, but is this uniform in the sense that the probability that the vector lands within a particular region on the sphere that's going to be proportional to the area
Yes,
of that region?
that's
true?
exactly what it means, yeah.
And I don't care what the proof is. I'll leave that to you probably.
Because I don't believe that statement, that's why.
Oh.
I don't care about the proof either.
Okay.
So the first algorithm is widely used, but it makes an assumption that you have access to normal random variables, and sometimes you don't. So if you don't, then you're pretty much sunk with the first algorithm. So this is another algorithm that I found with the literature search, and we wish to create a vector of this form, vector u, and I don't know the proof of this, but in the article there was a proof that this is the form of the vector that we want. And once we have the thetas, then we will be able to calculate what the vector u is. And what they found in the article was that if u is uniformly distributed on the sphere, then the density, so they're talking about the density function. So the density function of theta I is proportional, so I'm gonna make K the proportionality factor, proportional to sine theta I to the n minus I minus 1 power on 0 pi. And for I is between 1 and n minus 2. And then when theta n minus, and then for theta n minus 1 is uniformly distributed on 0 to pi. And we can't generate from this function directly. So in the article, it was talking about using an accept-reject method for being able to generate the thetas. So I'll explain what exactly that means. So let's draw the density function here. So sine is usually between 0 and 1. So since we're multiplying by k, it's going to be between 0 and k. And we want it only between 0 and pi. So we can't just randomly pick a point from here and just use that point because, for example, the relative probability of this point should be a lot less than the relative probability of this point because it's a lot higher. So what we do is we use an accept-reject method. So you take a randomly generated point, which is from 0 to 1, and it's uniformly distributed, and then you multiply by k, because u is between 0 and 1, and then when you multiply by k, it'll be between 0 and k. And we want the probability that we accept to be here, and then we want to reject here, because this point is very low, so we don't want to really accept it that often, because we should be accepting a lot more here to try to generate the distribution that is represented by the curve. So we take KU and then we compare it to the function. And then if it's less than the function, then we accept because it's in this region. And if it's greater than, then we reject and it's in this region. And if we reject, that means that we try again with a different point here, and then we keep going until we accept a point. Oh, and also you can just cancel out the case here. So you can just compare the random number from 0 to 1 that's uniformly distributed and compare it to this function. So this is the code for just generating one angle. And what we do is pretty much what I was talking about here, where the first thing is we create test and we initialize it to false. And we first create theta, which is going to be our result, which is what we're returning, but we initialize it to be an empty matrix. And we do a while loop. While we haven't found the angle yet, that's what test represents, that we found the angle. We create two uniformly distributed numbers between 0 and 1 called u and v. And then this value t is this right here. This is t. And notice that we're passing in a parameter called p to this function. So when you're passing in the value p, you want p to be equal to n minus I minus 1 so you can represent that distribution correctly. And we're doing the same calculation here that I had. If u is less than t, that means that we accept the angle that we have. That means the test is true and then we stop looping. But if it's false, so if this isn't true, that means we don't go inside the if. We don't set test to true. So test remains false, and then we keep looping until we do find an angle that works. So we're going to treat that as a black box function for right now, which means that we're not going to go into the logic of that, because here I'm using it, but we're just going to accept that it creates an angle that's on this distribution here. So I'm really proud because I wrote this code. And so how much time's left? Because I have an example for using this, but I don't know if I have time.
It's got about 20 minutes.
Okay. So what I'll do is, instead of using numbers, I'll just show how we generate something similar to this, because that's what we really want. So I'm going to do it in 3 dimensions. So what we want our vector u to be is this. And I'm just going based off of what it says vector u should be. So this is d is 3. That's what we want our result to be at the end. So first we start and we create our matrix of thetas. So we're just looping, and here we're looping from I is 1 to n minus 2. And here I'm using n as my dimension. So here n is going to be 3. And I'm creating a matrix of theta. And it's going to be a matrix of zeros initially, and it's going to be 2 by 1 initially. And what I'm doing is, in the for loop, I'm doing the for loop once, just looping once, and I'm using the function from before to get a random angle. And then afterwards, I'm finding another angle, because for this one, we have a special case where we just want it uniformly distributed from 0 to pi. So that's what that line's doing. And instead of putting numbers, I'm just going to use symbols. And then the next line says that we want to set the sine equal to the sine of these angles. And the next line is that we want to first take the cosine of those angles and then flip it and set that equal to cosine. So the first thing we want to do is we want to do the cosine of each one. So we want to flip the following: cosine theta 1, cosine theta 2. And what it means by flipping is that the top becomes the bottom and the bottom becomes the top. We're just flipping them over. So it's equal to cosine theta 2, cosine theta 1. And then the next step is that we want to add a 1 to the top. And we're just And then the next step is that we're creating a diagonal matrix and send it equals cosine, where the values on the diagonals are these values. And then the next step is we're creating the vector that we're going to be returning from this function, and we're setting it initially equal to a 3 by 1 matrix of ones. And now we're going to do the for loop, and we're going to loop 3 times. And the first time we set b equal to sine from 1 to n is 3 and I is 1. So from 1 to 2, comma 1. So that means that we're going to be taking the first 2 rows in sine, which are these 2. And then after that, we set u of 1, 1. So that's the first row, the first column, equal to the product of these 2 rows, which would be sine theta 1, sine theta 2. And then if you notice, that's what we are supposed to have, so that's good so far. And the next time we loop, we have B is the sine matrix from 1 to 1, comma 1. So we're just taking the first row of sine, which is just sine theta 1, and then we set the second value in the U matrix to be equal to the product of the values in here, which is just sine theta 1. And that's what we're supposed to have, except we're going to be multiplying by cosine of theta 2, which is what we have here. So eventually what we're going to be doing is multiplying this matrix with the matrix with the items from here, but it's going to be a diagonal matrix. And the last time we loop, we take the sine matrix, but the thing is that here we're taking nothing, so it's just an empty matrix, and the product of the empty matrix is just 1. So that means that right now we have as our u so far sine theta 1, sine theta 2, sine theta 1,